In this video, we'll explore the 1 Santims coin from 1924, a remarkable artifact from Latvia's history. Minted during the era of the Latvian Republic, 1918 to 1940, this coin represents a period when the newly independent nation was carving out its identity and rebuilding after World War I. Let's dive into its story and uncover the details of this historic piece. Before placing this coin under the Electron microscope, let's take a closer look at it with the naked eye to appreciate its design and details. The reverse of the 1 Santims coin, minted in 1924, features the denomination and year. Made of bronze, this coin reflects the craftsmanship and symbolism of Latvia during its early years as an independent republic. The obverse of the coin features the national coat of arms of Latvia proudly displayed above a flowing ribbon, symbolizing the strength and unity of the nation during its early years as an independent republic. Adopted in 1921, the coat of arms represents Latvia's unity and sovereignty. The shield is divided into 3 sections, reflecting the country's historical regions: Kurzeme, Courland, Vidzeme, and Latgale. A radiant golden sun at the top symbolizes freedom and independence, while the red lion represents Kurzeme and Semigalia, and the silver griffin stands for Vidzeme and Latgale. Surrounding the shield are oak leaves, symbolizing strength and resilience, and the ribbon below often features the colors of the Latvian flag, crimson, red, and white, representing patriotism and the struggles for independence. Together, these elements embody Latvia's rich history and aspirations for a united and free future. Let's place the coin into the electron microscope chamber and expose it to the electron beam to uncover its fine, intricate details. Let's start exploring the coin at 1 keV in the scanning electron microscope. When we examine the coin at 1 keV, kilo electron volt beam energy in the scanning electron microscope, we enter a fascinating realm of surface analysis. At this low energy, the electron beam interacts with the very top layers of the sample, making it ideal for studying the surface structure, fine details, and delicate features that might otherwise be obscured at higher energies. Let's dive into what this low-energy investigation reveals and why it's a critical step in understanding the history and condition of the coin. Why 1 keV energy is important. At 1 keV, the electron beam penetrates only a shallow depth of the material, typically a few nanometers into the surface. This low penetration depth makes it ideal for detecting surface topography without interference from deeper layers. For a coin like this, it allows us to clearly observe the effects of time, including corrosion layers, patinas, and even microscopic contaminants that have adhered to the coin's surface over the decades. Unlike higher beam energies, which may excite signals from deeper within the coin, 1 keV primarily focuses on the surface-emitted secondary electrons. These electrons are highly sensitive to surface features like scratches, dents, and fine ridges, giving us a sharp and detailed image of the coin's topography. Revealing corrosion and patina. Coins, especially ones as old as this, often have a layer of corrosion or patina formed over time due to chemical interactions with their environment. The electron beam at 1 keV allows us to closely examine these layers without damaging them. Corrosion can show us the types of materials the coin has been exposed to, perhaps moisture, soil, or certain atmospheric conditions. For example, we might see evidence of oxidation, which is common with bronze coins like this one. The patina, often a result of natural chemical reactions, can also reveal the coin's history. Its texture, thickness, and composition give us clues about the environmental conditions where the coin was stored or buried. For historians and numismatists, understanding this layer is key to determining the coin's authenticity and conservation needs. Uncovering fine surface features. With 1 keV energy, the secondary electron detectors pick up even the smallest details. We can visualize fine scratches, dents, and wear patterns that tell a story about the coin's journey through time. For instance, scratches might indicate the coin was used heavily in trade or handled frequently. Dents could show it was dropped or struck against hard surfaces during its circulation. Microscopic ridges and grooves can highlight the original minting process, revealing details about how the coin was struck and its design intricacy. These features are not just aesthetic. They serve as historical markers, helping us piece together how the coin was used and preserved. Identifying manufacturing details. Low-energy beams also help us investigate the minting process of the coin. By closely examining the die marks and surface patterns, we can identify subtle imperfections or unique characteristics that reveal how the coin was made. Coins from the early 20th century often have telltale signs of the minting technology of that time, such as striations from the die or slight variations in the design due to manual adjustments. Additionally, any micro cracks or stress marks on the surface might indicate the wear and tear the coin endured during minting or its time in circulation. These microscopic details allow us to reconstruct the craftsmanship and technological advancements of the era when the coin was minted. Surface composition and contaminants. At 1 keV, the beam can highlight surface contaminants or foreign particles that might have settled on the coin over the years. These could be residues from handling, environmental deposits, or even conservation attempts made to clean or preserve the coin. Studying these features can give us a better understanding of the coin's condition and how it has been treated over time. Interestingly, contaminants can sometimes serve as an additional clue to a coin's journey. For instance, soil particles or mineral deposits could indicate that the coin was buried for part of its life, while certain residues might suggest it was stored in a particular environment. Advantages of low beam energy. Using a low-energy beam like 1 keV has several advantages. First, it reduces the risk of sample damage, especially important for historical artifacts like this coin. High-energy beams can cause heating, charging, or even physical damage to delicate samples. At 1 keV, the beam is gentle enough to preserve the integrity of the surface while still providing detailed imaging. Another advantage is the ability to minimize charging effects on non-conductive parts of the coin, such as oxidized regions or dirt deposits. Charging occurs when electrons accumulate on the surface, creating bright spots or distortions in the image. By keeping the energy low, we can reduce these effects and produce clearer, more accurate images. Connecting the findings to history. What makes this investigation truly exciting is connecting the microscopic findings to the coin's historical context. For example, patterns of wear might reveal whether the coin was heavily circulated or kept as a keepsake. Corrosion layers and patinas might tell us about the environments the coin encountered, perhaps buried in soil or stored in humid conditions. Manufacturing details could highlight the minting technology of the time, giving us a glimpse into the industrial capabilities of the early 20th century. By examining these features at 1 keV, we not only uncover the physical story of the coin but also place it within the larger narrative of its time. This investigation bridges the gap between science and history, offering a unique perspective on a small but significant artifact. Now, we're moving to 30 keV, a much higher beam energy in the electron microscope. At this energy, the electron beam penetrates much deeper into the material, allowing us to look beyond the coin's surface and uncover details about its composition, internal structure, and even subtle manufacturing secrets. While 1 keV gave us incredible insights into the coin's surface, 30 keV opens up an entirely new layer of discovery. What does 30 keV do? At 30 keV, the electron beam has significantly more energy, which means it can interact with the atoms deeper within the coin. This beam energy is ideal for generating backscattered electrons and characteristic X-rays, which provide detailed information about the coin's material composition. With this energy, we can explore not only the alloy the coin was made from but also any impurities, corrosion products, or unique material features that lie beneath the surface. What's particularly fascinating is that this level of penetration allows us to identify how the materials were mixed during the minting process. For instance, we might find tiny differences in the distribution of elements like copper, tin, or zinc in the bronze alloy. This can tell us whether the coin was made from a high-quality, well-mixed alloy or if imperfections were introduced during production. The historical story behind higher energies. The use of high-energy beams like 30 keV in electron microscopy revolutionized materials science and archaeology by making it possible to study the inner structures of historical artifacts without destroying them. In earlier times, analyzing the composition of an artifact like this coin would have required physically cutting it apart or chemically altering it, methods that would damage or destroy a valuable historical piece. With 30 keV, we can non-destructively uncover the hidden layers of the coin, preserving it while learning its secrets. For example, using this beam energy, we might uncover subtle traces of the coin's interaction with its environment. Imagine this coin traveling through trade routes or being buried underground for decades. It's possible that chemical reactions between the metal and the soil left invisible traces that are now detectable with this energy. Each element within the coin interacts with the electron beam differently, giving us a unique fingerprint of its history. What can we see at 30 keV? The first thing 30 keV reveals is the atomic number contrast using backscattered electrons. In simpler terms, heavier elements like copper appear brighter, while lighter elements like tin or zinc appear darker in the resulting images. This allows us to map the distribution of elements across the coin, showing us how the alloy was formed and how evenly the metals are mixed. Imagine zooming into the coin and finding that one area is slightly richer in copper while another has more zinc. This tells us about the production techniques used in the mint. Was the minting process precise and uniform, or do we see evidence of imperfections in the mixing of the metals? These insights reveal not only the craftsmanship of the time but also the resources and technologies available when this coin was minted in 1924. Exploring corrosion depth. At this energy, we can also investigate the depth of corrosion that might not have been visible at lower energies. While 1 keV highlighted the surface oxidation, 30 keV allows us to look deeper into the layers of corrosion and see how far the chemical reactions have penetrated into the metal. This can help us determine the environmental conditions the coin experienced over time, whether it was buried in acidic soil, exposed to moisture, or stored in a more controlled environment. Interestingly, corrosion can sometimes trap small particles from the coin's environment, like grains of sand or even microscopic biological remnants. These can become visible under the high-energy beam, adding more context to the coin's journey and the conditions it endured. The 1 Santims coin from 1924 bears the artistic touch of Rihards Zariņš, one of Latvia's most renowned engravers and graphic artists. Zariņš was instrumental in shaping the visual identity of the young Latvian Republic during its formative years. A master of fine detail and symbolism, his work often incorporated traditional Latvian elements, blending them with contemporary design principles. Beyond his contributions to coin design, Zariņš is celebrated for his role in creating Latvia's national currency and his efforts to immortalize Latvian culture through art. On this coin, Zariņš left his personal mark, his engraved signature, a small but significant detail that speaks to his craftsmanship and pride in his work. Using the Electron microscope, we can zoom in and examine this signature in stunning detail, revealing the precision and care Zariņš brought to every stroke. The intricacy of his engraving not only highlights his exceptional skill but also connects us to the artist himself, offering a glimpse into the passion and dedication that went into creating a piece of history. Thank you for watching. If you enjoyed learning about the coins and their fascinating history, please don't forget to like this video, subscribe to the channel, and share it with others who love history and coin collecting. If you'd like to support my work and help me bring you more content like this, you can also buy me a coffee. The link is in the description below. Your support means the world to me and helps keep this channel going.